and record this as well. Okay, I don't want to do that. I don't want to end it yet, at least not yet. Okay, let me share my desktop. And let's see, if you have any questions, as we're going through stuff, just kind of raise your hand. There's kind of a raise your hand function in Zoom. And then two, or you can also just kind of just talk, and I'll kind of stop wherever I'm at. So we're talking about, well, basically we're talking about visual and auditory processing, meaning the way in which we take in a visual information and how we make sense of a visual information. And if you think about the amount of kind of different sorts of things that we see in the world. So like if you just look at a regular landscape, there's trees, there's grass, there's maybe a cloud or a mountain. There's a lot of different things that we have to distinguish, both in terms of depth as well as color. And then obviously what something is, like trying to define and understand what something actually is. And so a lot of what we'll be talking about today is how we see something, and then how we recognize and interpret and explain what that thing is. So there's a few different things that we'll be looking at. So the basic idea of looking at a visual scene is a type of perception. We're perceiving the world in some way. And we both have to recognize certain kinds of objects. We have to see objects and know what they are. And then we have to recognize certain kinds of patterns as well. And to a certain extent, we have to make sense of the patterns that we see. One of the basic aspects of a visual processing is that we make sense of patterns based on past experiences. Even stuff that may be somewhat ambiguous, we will make sense of it, look at the pattern that we're looking at, and make it into something that makes sense to us. So there's a few different there's a few different things to think about here. One is the distal stimulus, and that's the actual object that we're looking at that is in some sense external to us. And then the proximal stimulus is the stimulus that we make up in our own minds. So it's the way we represent something outside. So a distal stimulus is something outside of us, something that we're looking at. And then the proximal stimulus is the way we represent that within our own minds. And that representation is going to take different shapes based on what we're doing with it, how important it is to us, and it's what types of actions we can do with it, and several different sorts of things. So on the retina, which is where we receive most of our visual information, the proximal stimulus is based on retinal neural activation. So what I want to start off in talking about visual processing is give kind of a review of kind of the neuroscience, or more of the biopsychology of how visual processing happens. And we're starting. So we'll start with the eye, and the eye contains two different types of sensors, and those are rods and cones. And so rods are the most kind of spread out within the retina, meaning they're the cells that are the most prevalent within the retina. And then cones are much smaller, and they deal with much more kind of detailed sorts of information. So rods are kind of more of your detectors, and then cones are more for focusing. So cones are able to detect fine details, and they allow color perception. And then rods function much better in a dimmer light, and can more kind of detect what something is. So the way in which the eye works in general is the rods kind of detect different sorts of things that we see within our environments. And then the cones allow us to kind of focus in on something, to actually see something and see the details. See the details that are contained within a particular visual object. Now, the basic visual pathway is that information that enters into your right eye is processed by the left side of your brain, and then information that enters into your left eye is processed by the right side of your brain. So the information goes in, crosses what's known as the optic chiasm, moves through the lateral geniculate nucleus in the thalamus, and then moves into area V1 of the occipital lobe. So that's the basic road map or kind of roadway through which visual information enters into the eye and moves towards the back of the brain into the occipital lobe. One important thing to kind of know about how we process visual information is we don't really see with our eyes, we see with our brain and our body to a certain extent, meaning that most of visual processing doesn't really happen within our eyes. The eyes take in that first part of the distal stimulus. But then the brain is what kind of processes all of that information and begins to make sense of something. So we don't really recognize what something is until that information has gone much further back within our brains. Now, the occipital lobe is actually further subdivided beyond area V1 into several different sub areas, such as V4, which responds to color, V5, which responds to movement, the area TEO, which is involved in color discrimination, as well as 2D pattern discrimination. And then a TEO projects to area TE. And then in area TE, neurons here respond to 3D objects, such as a face or a hand. So the occipital lobe has several different sub areas that process different kinds of visual information. And how we know this is because of the work of Hubel and Wiesel. And what they did back in 1979 was they discovered certain kinds of feature detector cells within the cat cortex, within the visual cortex of a cat. And they did that by kind of sticking in very small needles with electrodes that actually recorded the neural firings of several different neurons within the cat brain. What they found is that different neurons respond to different kinds of features within the environment. And so within the early processes within the cortex, it starts within the occipital lobe, and then it moves further on into different areas to further process certain kinds of visual information. And the primary areas that it moves to are called association areas. And association areas are what create our more complex sorts of visual objects. They're what kind of detect more kind of advanced or complex sorts of visual objects. So the way that we talk about the visual association cortex is we talk about it in terms of two different streams. One is the dorsal stream, and one is the ventral stream. And the dorsal stream basically goes up from the occipital lobe up to the parietal lobe, and it's primarily involved in where an object is, whereas the ventral stream starts at the occipital lobe and moves into the the temporal lobe, and the ventral stream is a little bit more involved in what an object actually is. So that's the kind of basic kind of overview of what's happening in the brain. What most of cognitive science does, or what most of cognitive science does is focuses more, once we're in those association areas, how do we make sense of what it is that we're looking at? How do we begin to kind of understand and process what it is that we're looking at? Okay, so I'm going to jump over face perception for now. But is there any questions over the basics of visual processing in the brain? Okay, so let's move on to kind of a little bit more strictly cognitive science sorts of things, which is thinking about how do we make sense of the visual information that we see? How do we categorize that? So there's a few different types of principles. One is this idea of Gestalt psychology. Gestalt psychology. And this is the idea that when we're looking at something visually, we're making sense of both the figure and the ground. So the figure is something that sticks out to us, that's distinct from the ground. Now what happens when we have what's called an ambiguous figure, like we have here, is the figure and ground kind of switches back and forth to where you're either seeing two faces or you're seeing a vase. And what our brains do is, in some ways, we kind of switch back and forth between the two types of scene. We kind of make the blue ground and the white our figure, but then because the object looks so similar to a face as well, you can have what's called a Gestalt switch, to where suddenly what was the ground becomes the figure, which is these two faces, and then the white becomes the ground. There's a lot of different different examples of this. But the way in which we often make sense of things is we take the whole scene into account, and then we begin to organize it based on figures and grounds. Okay. Now, the other thing that we see in terms of a Gestalt is what are called illusory contours. Illusory contours. And this is where we will see lines or see the contour of something that isn't actually there. And it's the way in which our own visual perception fills in certain kinds of missing information to make sense of what it is that we're actually looking at. So when you look at this figure, you'll start to see this kind of white triangle that's kind of in the middle of all these other figures. Now, what you'll notice is that the triangle itself isn't actually there. What we have is three different figures that kind of partially make up this other triangle, but our mind naturally tries to make sense of things that are not fully completed and completes the figure for us. So these are sometimes called illusory contours. And this is the idea that human perception is more than the sum of the information in the distal stimulus. So we have 6 different aspects of this distal stimulus that we make into a more complex whole. And it's that a complex whole, and it's really a part of cognition is trying to make sense of what we're looking at. And even if something is somewhat ambiguous, we will often make it non-ambiguous, meaning we will kind of make sense of it as best we can, and then believe that we're seeing something that maybe sometimes wouldn't be there. And that's what a lot of kind of visual illusions are kind of like that. It's something that isn't really there, but because visual perception is so interested in pattern completion, we find a way to kind of make a whole out of something that isn't quite a whole. All right, any questions there? Okay, so now we're going to move a little bit more into how different theories about how we recognize what something is. How do we find out and kind of figure out what something is? So here's kind of a certain kind of problem. Now you should be able to read that this is cognitive psychology, okay? But if you notice, there's several different, very different representations, visual representations of these two words. And yet we're able to kind of see the same thing, even though very different kinds of visual representations are actually being shown. So this is one of the challenges. One of the ideas is we use a certain template. So we take a template about what something is, and then we match that template to what it is that we're looking for. Let's see, I think one of the things I've already talked about, see in here, is like a bird. So we have a template of what we think a bird is. Maybe it has feathers, let's see, it has wings, let's see, it has a beak. So whenever we see something, in the world, we take that template and we match it and we say, is it the same or is it different? So the problem, though, that comes up is one that we're seeing right here within this slide, is there's a lot of different, it would be hard to have a single template for all these different kinds of words. You also run into the same kind of problem even when we're talking about birds. There's certain birds that'll fit the template that we have, but then there's other birds that are so different that it becomes much more kind of difficult to know whether or not it's the same or not. There's a lot of things that don't always match the particular category that we're looking at that can sometimes make it a little bit more difficult to simply use a template alone. So templates are probably not what we use oftentimes for certain kinds of a visual perception. But there may be other more kind of elementary or kind of basic sorts of processing that we'll talk about a little bit later that actually uses templates. Now the other, another theory about how it is that we see things is called the feature analysis theory. And this is the idea that we look for distinctive features when we're looking for when we're trying to kind of figure out what something is. So for example, we could compare a new letter. So it's said that we're looking at a particular language, and we compare that letter to a stored list of distinctive features. So we have we have several different kinds of objects. Each of those objects has a distinctive feature that makes it the case of what that letter actually is. And so here's the example that actually she used when she was doing this particular research. So we have several different letters here, A, E, F, H, I, L, V, W, so on and so forth. And then we look at what types of things, what are distinctives about each of these letters. So do they have certain types of horizontal lines or vertical lines, diagonal? Is there a closed curve, or is there any type of asymmetry? And so we use, based on the distinctives of kind of each of those letters, that's how we kind of figure out what each of those letters are. And there's a certain amount of empirical evidence that actually seems to suggest that this might be the case. So Eleanor Gibson was the first one to kind of look at and kind of see how people may make distinctions in terms of letters. And what she looked at was the time required to decide if two letters are different. And what she found is that letters that share the same distinctive features take longer to discriminate. So it's harder to tell the differences between like a P and an R, because a P and an R share so many things in common. So they have, so they both have a horizontal line. They both have that curved line, and then the R just adds this one kind of tail to it. Whereas an O and the L are much easier to decipher because the shapes involved in them are so radically different. An O is nothing more than a large circle, whereas an L is two distinct lines. So that seems to give a certain amount of evidence or weight to what Eleanor was up to in terms of her research. And it is probably the case, even if the feature, even if the distinctive features isn't exactly right, it is the case, and we'll see this kind of overall more and more, the closer things are, they often are much harder to distinguish, whereas the further or the more distinct things are much harder to tell, are much easier to tell that they are not the same thing. And that'll be kind of something that we'll see kind of often. One other thing about kind of looking at these different theories is most likely in terms of visual processing, we use several of them. So we never use, there's no one way that we process visual information. Depending on the kind of visual information that we're processing, what it is that we're looking at, what it is that we're using that for, it's probably gonna, different kinds of cognitive systems are gonna be in play that will help us to actually understand what those things are. And we'll see that a lot, both in terms of visual processing, knowledge representation, and several other facets of cognitive psychology. Okay. Now, it was also the case that Hubel and Wiesel actually kind of noticed something very similar. And that was that larger distinctive features cause more neural activation, meaning that the bigger the distinctions were between two things, the more neural activation that you had, thus signaling quicker a bigger distinction between the two things that you're looking at. So it seemed to be the case that this idea of a feature analysis, of a feature analysis is really going to be working, especially at kind of the lower levels in terms of visual processing. Okay, questions?
What would this kind of theory look for people with like dyslexia or things like that? Because I'm assuming for them, this would be a lot harder with changing letters.
I'm sorry, say that again.
I was just wondering about like people with dyslexia.
So it depends. Dyslexia is more about the way in which letters get almost written onto a person's mind, more so than something as basic as kind of general feature of a detection. So, and I believe, and I don't know as much about how dyslexia works, but I believe that their brain kind of automatically like switches letters. And so the same process could still be going on. They might not be like better or worse than that, but dyslexia is probably something that happens a little bit further down, is what I would think. Because it's probably less about, it's the way in which they encode letters that something goes haywire, more so than not being able to kind of distinguish different types of features. See, unless you've heard something different about that. I'm not a huge expert on a dyslexia, but I would think it'd be something a little bit further down the line. Any other questions? So some of the problems with feature analysis theory is it makes sense in terms of things like letters and things that they're really kind of strong distinctives. But when you look at things in nature and the kind of shapes you have in nature, there's much more complexity to the shapes that we see, such that trying to whittle it down to a particular feature would be kind of difficult. So we see a lot more complex shapes. There's a lot more kind of overlap in terms of different sorts of features. And then we can have, and then there's a certain amount of a distortion that happens as well when something moves. And so feature analysis seems to work with things like letters and maybe with language, and probably some other things as well. But when we look at other kinds of objects, it seems like it might not be as good of an explanation for kind of different sorts of a natural shapes, if you will. And that's where this idea of recognition by components theories actually comes in. And this was developed by Irving Beardman. And what he thought is that objects that we perceived are made up of what are called geons. And a geon is a basic 3D shape. And that when we look at different things in the world, we combine these basic geons into a meaningful object. Also, it's the case that some amount of fMRI research seems to suggest that areas of the cortex beyond the primary visual cortex actually respond to geons. And that would be the different association areas. And the association areas are where object recognition truly happens, meaning deciding what something actually is. So here's an example of a certain kinds of geons. So you can see that on the left, these are more of these basic kinds of objects: squares, cones, cylinders, pyramids, and that the geons make up different kinds of objects that we see, like a flashlight, a suitcase, a coffee cup, a pail, so on and so forth. So this is kind of another way, rather than focusing on distinctive features, it could be the case that these objects are made up of more basic objects that we hold within our minds. And those geons are kind of put together almost like Legos to make up the different objects that we see. Now, some of the modifications, though, that need to go in when thinking about this particular kind of theory is we need to account for a quicker recognition when a standard viewpoint is compared with a different viewpoint. One of the difficulties that comes up is, when you're looking at an object, let's see, depending on its particular orientation, that will affect how easy it is to actually recognize it. So when you see a pail and let's see, from a certain orientation that kind of clearly shows both the pail and the handle, it's very easy to see what it is. But when you're looking at it from, say, like the bottom or for the top, it's much harder to kind of know exactly what it is. So the geon theory runs into problems in terms of how do you recognize what something is when you're not looking at it from a more kind of standard perspective. Now, we're actually pretty good at actually recognizing something from a weird perspective, but it does take us a little bit longer. One of the things that seems to be at work in those kinds of areas is actually mentally rotating something. So when we don't know exactly what something is, we actually have to mentally rotate it in our minds to actually figure out what it is. Now, one of the possible ways to account for this is this idea of a viewer-centered approach. And that's the idea that we store multiple views of different kinds of objects rather than just a single view. And in some ways, this kind of makes sense. So if we think about objects that we see all the time, and we have a certain kind of a conceptual memory for them, we have several different pictures of kind of how those objects actually work. So we have several different kind of viewpoints of different times that we've seen, like a pail. or a phone or whatever it might be. And so we do have a certain storage of different orientations for a particular object that we store within our own minds. And that could be part of what's going on there. And it's a way to kind of overcome that a particular problem. But here again, it kind of shows that to a certain extent, each of the theories that we're talking about has certain kinds of limitations. And it may be the case that we employ different kinds of visual processing theories or kind of different types of methods, depending on what it is that we're looking at and the situation, and maybe even the type of orientation that we're currently looking at as well. Okay, questions? Okay, so who can give me a definition of what bottom-up processing is?
Is it when you see something and then it goes into your mind and then that's when you process it?
Kind of.
Yeah, so it's like having an external stimulus and then you internalize that, so it would be bottom up kind of thing.
Close. I mean, it's more about a bottom-up process is emphasizing the distal object. So in processing, it's kind of emphasizing what is external to yourself, because it's all about what is first hitting your senses. So in a way, bottom-up processes often starts visual identification, but bottom-up is more about the external object and the features that it's sending to your senses. Okay, how about what is bottom-up processing? I'm sorry, I just said that one. How about what is top-down processing? How about, oh, yes, Giselle.
Oh, I was gonna say, I remember it being something about like, coming up with like information based on like what you already know, like knowledge and like experiences. Like I remember from one of my other classes, like we were talking about it, like something about like if like you write a word and like part of the letter smudge, like you can fill in the blanks and like you can kind of figure out what it means. Maybe if you're familiar with what they're trying to say.
Good. Yeah, that's getting at it. So top-down processing is using your own experience to both fill in, as Giselle was saying, kind of fill in any kind of missing information, but also it doesn't just fill it in, it also helps you to quickly identify what something is. Bottom up and top down processing are always working in tandem with each other. And when we have so much experience with different kinds of objects, that's what allows us to so quickly recognize what something is. So that when we initially see a particular distal object, we immediately begin to process it based on past experiences that we have. So it's never the case. So there's, if I guess you'd say the first time you see something, there may be a little bit more bottom up processes involved, but most of the time we're doing kind of almost a dance between each of these processes because they both have to be at work, because you both have to see, you have to see something and it has to actually hit your different sensory receptors in order for you to see it. But then our top-down processes are what allow us to go, oh, I know what that is because I've seen a million coffee cups or iPhones or whatever it might be. So it's that way in which those processes work together in order to allow us to quickly identify different kinds of information.
So would an example of that be, for example, like a child who sees for the first time a cat but knows how a dog looks, that like that child would more use like bottom up processing, but then would come to the conclusion that it's probably a dog because of their top down processing?
Yep. So see if I'm following your example, if you had a child that grew up with a dog and then saw a cat for the first time, they could very easily call it a dog, because as far as they know, all kind of pets or all kind of animals that they've seen, they will often use that top-down information of the dog as a way to identify the cat. And so that'd be a great example of a top-down processing, because the child has only had experience with a certain kind of animal, they kind of assume that all other animals are that same kind of animal. So yeah, that'd be a great example. Okay, other questions or comments? So then to kind of review this a little bit more, so top-down processing is strongest when, when a stimulus is registered for just a fraction of a second. So when we see just a quick flash of something, we use more top-down processing, because here again, we're kind of having to fill in what we've seen. We're having to kind of just based on that kind of quick flash, we have to kind of just interpret it as best we can. The top-down processing is also strong when stimuli are either incomplete or ambiguous. And that's probably what's probably happening if we go back to the kind of face and vases example, is our top-down processes are kind of imposing a certain kind of pattern, a certain kind of a pattern recognition onto this object that allows us to either identify it as a vase or two faces. And so top down, we probably go back and forth between seeing the vase and seeing the faces. And so the top down processes are what allow us to kind of have two different kinds of organizational perceptions of this particular object. Okay, secondly, top-down processing is also strong when stimuli are incomplete or ambiguous. I just said that. But object recognition combines both bottom-up and top-down processing. We kind of talked about that already. Okay, so a few other examples of this. One is the role of a top-down processing and reading. So can anybody read this particular sentence here for me?
The man ran.
Yeah. Now, most people, when they're given this particular stimuli, find it very easy to read this particular sentence. The man ran. But notice how the H and the A are the same exact symbol in each case. Okay, so this symbol or this letter is the same as this and the same as this. But most people do not even perceive them as being the same. In fact, some people would even kind of almost finish each of these A's as they're reading this particular sentence, because that's the way in which we interpret what the sentence is. We take ambiguous information and even stuff that doesn't exactly make sense, and we make sense out of it. So we can still manage to read this particular sentence, even if each of the middle letters in the word has been rearranged. And this is known as the word superiority effect. The word itself kind of overcomes, or kind of, our definition or understanding of what the word is and what it means has a top-down influence on the distal representation of each of those words. That's also part of the reason why we're able to read so fast as well is because we're actually able to kind of judge what words are most likely to actually come next. Whether something's going to be a subject or a verb or those kinds of things. And top down, we're kind of predicting what we're expecting to actually see next. And that's what allows us to kind of skim and go so fast through different kinds of readings. Okay, so for this next sentence, I don't know if I'm going to do that right. Oh, well. Okay, can anybody read this? I see this sentence up at the top.
The boy could not solve the problem, so he asked for help.
Good. So if you notice, could is misspelled, solve is misspelled, problem is misspelled, and asked. And what's interesting is normal sentences that don't have these spelling mistakes are read at about 250 words per minute. But even when you have misspelled sentences, you're still at 227 words a minute. So what's interesting and what's probably happening is when we're reading, we're processing words at a much more complex level, at more of a meaning level, such that we're not paying a whole lot of attention to the individual spelling of each of the words. We're trying to get to the meaning. And so because of that, these don't have to be perfectly spelled. This is probably also why we have so many misspellings when we're writing and how we can miss certain words that are actually misspelled. Like, have you ever written a paper, thought that it was perfect, and then you get it back from your professor or from the TA and there's all these mistakes. There's grammar mistakes, there's spelling mistakes. That's because you were focused on the meaning of that paper and you weren't as focused on the misspells or the grammar or whatever it might be. And that's because at a certain point, you're processing that information at a higher level of complexity in terms of meaning and not as focused on the words itself, or well, on the exact spelling of the words. And it's funny because this happens to everybody. I write stuff all the time and I'll forget to add so you could add a certain word, forget to add a period, a space, like all these small little errors. But to me, it reads normal. It reads like this is exactly what I wanted to say. And it takes several times. That's why you have to edit a paper. It takes several times to actually go through the paper and get it to where you actually have it at that right level. Okay, questions or comments here? Now, the same can happen in terms of the content of a particular sentence. So the context of a sentence actually facilitates the recognition of what a particular word is in a sentence. And this is based on Ruckel and Oden's 1986 experiment, which is known as the bears and beans experiment. And what they showed is that both bottom up and top down processing operate in kind of a coordinated fashion in terms of understanding what a sentence actually is. So the stimulus was that either a lion tamer or a zookeeper or a botanist and a dairy farmer raised either bears and beans to supplement his or her income. So the subject changes how we perceive it, but then the accuracy of the primary stimulus word also changes how we perceive something. So if you look down here, here are the different letters that we're at of, let's see that we're at the end of either beans or bears, okay? So obviously here is a fully formed N, and here is a fully formed R. And then there's all these places kind of in the middle. And those places in the middle, whether or not you read the word as either beans or bears, was really dependent on whether it was a lion keeper or a zookeeper, or whether it was a botanist or a dairy farm in terms of the bear response. And so what that shows is both the context of the sentence. So whether or not the context matches the word that you're trying to identify, but then also how accurate the actual stimulus was as well. So if it was a really well-formed N, then you would not see it as a bear, and you would not necessarily interpret it that way as well. Okay. Okay, questions or questions or comments? Okay, so I'm going to get set up for the next part. Just give me 1 second. We're going to watch a video.
Graham.
Okay, so let me share the screen one more time. Okay, so let me just get this set up. So I apologize for.
Grammarly does more than catch errors.
Hey, can you guys hear that?
With Grammarly, you can find really good, no, perfect words. We've set up hidden cameras on the boardwalk to try and pull a fast one on unsuspecting grown-up brains.
Do you know where the subway is?
We've invited 2 actors to join us and ask people here for directions.
Excuse me, sir. Do you know where the metro stop is?
But when we switch out the person asking for directions,
Then where do you go?
how do you think these grown-up beach brains will react?
Great, thank
One,
you.
ask beachgoers for directions.
Sir, do you know where the metro stop is? What is it? The metro stop. I've been looking for it and I can't find it. I'm not from around here. I keep looking for it everywhere I go.
After one of our actors asks for directions, surf's up. We switch out the actor. You think our beachgoers will even notice?
You see that guy in the red truck?
Yeah,
See
I
them
do.
guys?
Yeah.
They'll direct you right away to the train station.
Oh, they will.
Side over there.
Right.
Right.
Okay.
To the left.
To the left.
If it seems like these beachgoers don't see the change,
Down here. It's going down that way.
it's because they don't. But if you think this game works because Bearded Guy 1 looks a bit like Bearded Guy 2, let's try the switch with a not at all bearded woman.
Can I ask you a question? Do you know where the? Make it simple. I'm trying to find the metro. The what? The metro.
That's a newspaper.
Is that in England?
It's a daily newspaper, yeah. Did you notice that they switched? You didn't say anything.
No. What's this all about?
So, do you think you'd fall for it? Well, give it a try. Look at this photo. Try to commit it to memory. Now we're going to interrupt it for a second. Can you detect the 3 changes we made to the photo? How many did you find? Did you see the added flock of birds, the change in color of the cup, and the now missing band around the hat? When you see the changes take place in real time, they're easy to pick out. But just a slight interruption can throw your adult brain's memory off. Don't feel bad if you didn't see these 3 other changes we made. With so many possible changes, your brain has to prioritize its attention. This is a phenomenon called change blindness, and it's the same thing that's happening on our boardwalk. So it may seem like an adult brain blunder, it has its benefits. Your brain's mission isn't necessarily to make an accurate picture of the world for you, but a useful one. And in this situation, the most useful thing is giving accurate directions, even if your eyes miss the person you're giving them to.
All right, let's do the find my. Okay, questions or comments? So what that was an illustration of is what are called smart mistakes in object recognition. And this is the idea of a change blindness. Change blindness is the failure to detect a change in an object or a scene. And so that was an example of what is known as Simon and Levin's Stranger in the Door study. I think they did that study maybe in the late 90s, I think it was. See, but anyway, it basically illustrates the fact that anytime we're looking at a certain, visual scene, we're only taking in so much information, and we're only, only a certain amount of information we're making kind of hard, or we're kind of holding it fast, or we're looking at the details of something. Most of the time, we're just getting the gist of what something is. And it's not until our attention begins to focus on like what someone's shirt was, or the color of their shirt, what they were wearing, those kind of things, that we'll actually remember those kinds of details. And if you even think about it, like if you try to remember like what your friend or your dad or your brother or your wife to your girlfriend, like try to remember what they wore yesterday, or what they wore like 2 days ago, or what you yourself wore. Even maybe 2 days ago. Like it's hard to remember a lot of those details. A lot of what we do when we're taking in visual information is we just want the gist. We just want the basic idea of kind of what's happening, especially for current kinds of processing. But however, if we pay attention, we can remember certain kinds of details, certain kinds of things that might have actually occurred. But we have to be paying attention to those things, or our brains simply won't pick up on that. Partially because there's just kind of too much information. You just can't, we don't have enough storage in our own minds to remember all that different stuff. And so we just have to only take in what's necessary for whatever it is that we're currently doing. So when we meet a stranger, it's the first time we've ever seen them. We don't know if we care who they are, or we'll ever see them again, or kind of have any need to actually know what they look like. So at first, we don't really take in a very distinct and detailed representation of how they look, or even their gender to a certain extent. because they're just asking you for directions. So for us, from our perspective, we don't really need to know the details of what it is that are going on. We just need to know kind of the basics. And so that's why even if you change it, you wouldn't really know, or you wouldn't really kind of, you wouldn't be aware that that change was actually happening. So a change blindness is a detecting the difference between two scenes. So the top-down processing encourages us to assume that the basic meaning of the scene will remain stable. And so this is one of the principles that a lot of visual processing really hinges on, is this idea that, you know, we assume that the world stays the same, that the objects in it and the things that we're looking at, but that there's a certain kind of constancy to what it is that we're looking at. Just kind of a basic assumption that we make. And that allows us to not worry about being too kind of overly focused on all the little changes that may or may not be occurring. That's why, let's see. Do you guys remember that book, Where is Waldo? That's part of the reason why it's so hard to find Waldo, is because he's lost in this kind of vast array of kind of several different visual features. And so it's hard to kind of, to actually pick them out, because we're assuming all of these different things about what it is that we're seeing, and trying to discriminate visually at that level of accuracy is just really hard for us. So, so we don't, most of the time, we do not store a very detailed representation of any typical visual scene that we actually see. Now, if it's an important change, if it's something that sticks out to us, if it's something that's kind of important to us, then we're much more likely to actually observe it and to actually see it. But in general, we will tend to not take in a very detailed representation of any scene that we're looking at on a day-to-day basis. Okay, questions? Okay, so let me bring up this second video. Okay.
Rich biodiversity of the Okavango Delta is protected in Botswana, but the waters that support it are not. Okavango Eternal is helping to ensure that biodiversity is protected across the entire region.
The brain is constantly bombarded by far more information than it can handle. If we tried to process all of it, we'd be completely paralyzed. As a result, we have to attend to only a small part of what's in front of us at any given moment. Sometimes attention can fail and we lose focus. This is what happens in what we call inattentional blindness.
Pay attention. You're about to be tested. For this game, you get to be the referee and judge whether the kicker is able to put the football between those two yellow uprights, 20 yards away. Tracking a small moving object at a distance might be difficult, so watch the ball closely. So, was the field goal good or not? As the replay shows, it's good. Pretty easy, right? But while you were watching the kick, did you happen to notice which cheerleaders took off their tops? If you're looking for the rewind button, don't worry. We'll do it for you. Yep, there they are. While you were zeroed in on the kick, you missed 3 cheerleaders stripping down at the bottom of the screen. Don't be surprised if you missed it. We took advantage of a loophole in your brain. If you could rewind real life, you'd be shocked at how often inattentional blindness causes you to miss things happening right in front of your eyes. For example, Have you ever pulled into your driveway and realized you don't remember a single thing about the drive home? We've all done that. Now, you can't blame your brain for missing the cheerleaders. It was busy doing exactly what we asked it to do, focus on the football. And it wasn't just your brain that had to focus. Your eyes had to do some focusing of their own. In order to smoothly track the moving football during the kick, your eyes had to stay continually fixed on a small, fast-moving object. In fact, your eyes do this for you thousands of times a day, from driving a car to watching a movie. It's called Smooth Pursuit. Smooth Pursuit is a survival tool hardwired into your brain. Long before there were teams called the Bears and the Lions, man had to survive alongside actual bears and lions. Smooth Pursuit helped our ancestors spot a fast approaching predator.
Okay, let me bring the other. So inattentional blindness is kind of a similar kind of process to change blindness. And it's just this basic idea that when we're actually looking at, just like we're kind of blind to a certain extent to certain changes that happen, we also are blind to changes that we're not currently attending to. So inattentional blindness is the failure to notice when an unexpected but completely visible object suddenly appears. The most famous study of this is by Simons and Chabris, and that's where they had this a basketball study. And what they did is they asked the participants in the study to kind of count how many passes, I think it was like 4 or 5 team members actually made. And what they often failed to notice was that there was a large gorilla that actually walked through the people as they were passing the basketball. And the idea is that because you're attending to kind of how many times that a particular basketball is passed, you just failed to notice this other change that's actually happening. Now, of course, this doesn't always happen. And if something sticks out enough, you will definitely recognize the change as it occurs. But it just once again shows our tendency to only take in information that is personally relevant or important to what it is that we're currently doing. And it's just the way in which when you're focused on a certain kind of task, other things you will just kind of not notice. You will not, because you're so focused on doing that one thing. So it isn't necessarily a bad thing, but it's just kind of a part of the way that we actually process information. So perceptual representations often change very rapidly. And so our visual system just simply cannot track all of the details that are occurring all the time. Now, our visual system is fairly accurate in creating the gist or the general interpretation of a scene, but we mainly just simply focus on what's important. We focus on what we're looking at. We're focusing on on the information or the task that we need to do, and we miss a lot of other sorts of things. And so this kind of fits with a theme too, such that our cognitive errors can often be traced to the use of a rational strategy. And the rational strategy, or the trade-off that our visual systems make, is that we focus on things that are important or relevant to us, and we let go of a certain amount of details for any visual scene that we're currently looking at. So it produces a kind of cognitive error side effect, that there's certain things that we miss. There's certain things there's certain changes, and there's certain things that we just don't simply attend to. And it just kind of shows that when we're taking in information with our visual systems, we aren't taking it all in. We're only taking bits and pieces of it. And we're kind of putting it together at a later time. Okay, questions or comments? Or any questions on kind of a visual processing in general? Okay, so I think rather than kind of jumping into speech perception today, I'm going to wait on speech perception and kind of jump into that on a Thursday. One thing I did want to go through really quickly, I covered this a lot more in a biopsych, but just because the chapter kind of refers to it a certain amount, there is a certain kind of a deficit that can develop in people, and that's what's called prosopagnosia. And prosopagnosia is the inability to recognize someone based on their face. I mean, you cannot use their face to actually know who they are. You use some other kinds of cues or some other way in which to identify who that person is. Facial recognition seems to be coordinated with what's known as the right fusiform gyrus in the inferotemporal cortex, which is a part of a general area of the brain that's involved in general object recognition. And the fusiform gyrus is this area right here. This area in blue. And that's another kind of interesting kind of visual problem. Well, it seems to be related both to certain genetic factors that people seem to be born with it, and it also might be related to certain kinds of a brain injury as well. Okay, so in that case, I think what I'm going to do